Section 15, comparing means. This is a little simpler in practice than Section 14, comparing proportions. In theory, it can be very complicated, but we'll stick to what we've been doing in Sections 12 and 13 when we talk about means, which is we'll assume that the population standard deviations are known. Otherwise, it could be very confusing, and we'll talk about it at the end of the course if we have time. So, comparing two means. This works very similarly to what we did in Section 14. We have two populations, and we take a sample from each. We want to know whether the average of the numbers in the one population is the same, plausibly, as the average of the numbers in the other population. So we'll organize our terms here. Population 1 has an unknown mean and a known standard deviation. Let's say the average age of everybody in New York State. So we don't know the average age of everybody in New York State, but we do know how ages in New York State vary. Population 2 with an unknown mean and a known standard deviation. So let's say the average age of people in Massachusetts. We don't know the average age of people in Massachusetts, but we do know how ages in Massachusetts vary. It may not be realistic to assume you know anything about the population, but it'll keep our procedures a little simpler until we can talk about it later in the course. We take a simple random sample from each, say 100 New Yorkers, size N1, and 200 people from Massachusetts, say size N2. In each case, we get a sample mean, the average of the numbers you pick from population 1, the average of the numbers you pick from population 2, x bar 1 and x bar 2. If we need them, we can also, given those 100 numbers or whatever, find the standard deviation, S, the Section 2 data standard deviation of those numbers. However, if we know sigma, we don't need it. If we don't know sigma, then theoretically we would estimate it with S. But that's another section. So as we talked about in Section 14, x bar estimates mu. In particular, sample 1 mean estimates population 1 mean, and likewise for 2. So the average age of the New Yorkers you pick estimates the average age of all New Yorkers. The average age of the people from Massachusetts you pick estimates the average age of all people from Massachusetts. So just as we did in Section 14, the logic plays out pretty much exactly the same. The difference in the sample means estimates the difference in the population means. For instance, if the difference in the two sample means is about 0, then it's plausible that this is about 0, that the population means are the same. If this is very different from 0, then it might be evidence that this is different from 0. If x bar 1 is a lot less than x bar 2, then that would be evidence that mu 1 is less than mu 2, and likewise for greater than. So our logic plays out exactly the same. We know that x bar is approximately normal shaped. There we go. X bar is approximately normal shaped for large N or for other reasons, centered at mu with a standard deviation of sigma over the square root of n. That's true for x bar 1, it's true for x bar 2. X bar 1, centered at mu 1, standard deviation sigma over the square root of n1. X bar 2, centered at mu 2, standard deviation sigma 2 over the square root of n2. So we know that if we subtract two variables, we subtract their means. And from Section 6, we know that if we subtract two variables, the standard deviations, we square them, add them, take the square root. So there's a little bit of algebra there. But if we take sigma 1 over the square root of n1 and square it, we get sigma 1 squared over n1. Likewise for 2, add them, take the square root. So logically, this is the sampling distribution of our statistic x bar 1 minus x bar 2, which is estimating this parameter, mu1 minus mu2. As in the previous sections, it's okay not to know this blank. That's what we're estimating. But if we know all the information in the second blank, I will get it. There we go. Then that'll make our procedures relatively simple. Otherwise, we'll talk about how to adapt them toward the end of the course. As before, if the sample sizes are very large, say 1,000, then we can substitute the sample standard deviations S1 and S2. If you know the 100 ages or whatever that you picked, then you know their average and you know their S standard deviation. So you've got those. If the sample size is very large, you can make those substitutions without any problem. And we'll call that standard error as usual when we estimate standard deviation of a statistic. But in this section, we won't be using that. We'll just assume that we have all of this information, and that'll make things a lot simpler. This just summarizes what I said in previous sections, that in any of these sections where a statistic is normally distributed, this will get a little complicated later in the course, but if the statistic is normally distributed, then you get the test statistic, which is z, by taking the statistic, subtracting your theory, and dividing by the standard deviation of the statistic. Or, as in the case of Section 14, the best estimate we had for it, the pooled standard error. In this case, we'll just simply use the standard deviation of the statistic. So our test statistic in this section will be z equals statistic minus theory about parameter divided by standard deviation of statistic. Our facts are organized exactly as they were in Section 14. Again, there's a lot of theories you could test about the sample means. You could test the theory that on average people in New York were 5 years older than people in Massachusetts, but you'd have to think about how that plays out with the algebra here. So we'll keep it simple. We'll have our H0, our null hypothesis, simply be that there is no difference in the two population means, or rather say that the difference is 0. In other words, that the one population mean is the same as the other population mean. The average age of New Yorkers is the same as the average age of people from Massachusetts. The average height of people in the United States is the same as the average height of people in Canada, and so forth and so on and so on. And we'll test that against our three usual alternatives, that mu1 is less than, HA being that mu1 is less than mu2, greater than, or not equal to. Same exact logic as in the previous sections. Our test statistic formula is, as we've seen, statistic minus theory about parameter, minus 0, divided by standard deviation of statistics. So there it is. The z in this section is computed by doing x bar 1 minus x bar 2 divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. As in section 14, notice that we're adding here on the bottom, so as long as you keep the proper sigma with the proper n, it doesn't really matter which population you call 1 and which population you call 2. The bottom will be exactly the same. And as for the numerator, it'll just change the sign. So, in section 14 and section 15, the normal pictures and the shaded regions start to do more harm than good. We streamline the process because the sign on the z literally doesn't matter. It just comes down to which way you've labeled things. Positive z if New York is 1 and Massachusetts is 2, negative z, vice versa. And by now you should understand that we are talking about a tail. So if the z is negative, look it up. If the z is positive, look it up and do 1 minus, or just make it negative and look it up. But a single tail for any of these hypothesis test sections, at least the ones that we've done thus far, a single tail is always less than half the area. Remember that. A single tail will never be more than 0.5. Two tails together? Sure. If a single tail is 30%, then two tails could be 60%. but a single tail will never be more than half the area. This just summarizes everything I've just been saying. So for a change, let's take an example where the result is more or less a foregone conclusion. All the heavy work was done in the previous sections. This is our fourth go at hypothesis testing, and this is our second go at these comparing hypothesis testing. So there's not a lot of theory that we haven't already done yet. Let's do an example for a change where we sort of know the answer. And that brings up a point. It's not about what you know or what you think you know. It's about what the sample allows you to conclude. Remember, H0 has the benefit of the doubt, and HA has the burden of proof. And small samples, for reasons we've begun to see, don't prove much of anything. So it's not about what you know. It's about what the sample allows you to prove. So let's check it out. Does regular beer have a higher percentage alcohol content than light beer? For a simple random sample of 108 regular beers produces an average of 5.12% alcohol content. A simple random sample of 83 light beers produces an average of 4.01% alcohol content. The regular beers that we happen to look at happen to have a slightly higher average alcohol content than the light beers we happened to look at. What does that prove? Well, it may not prove anything. Bearing in mind that prove is always a strong word in statistics, what does it provide evidence of? Maybe nothing, maybe something. For the sake of argument, let's assume that although we don't know how regular and light beers average, we do know how all regular beers vary, and we do know how all light beers vary. So for the sake of argument, our mu1, the percent average alcohol content for all regular beers, is unknown, but the standard deviation of alcohol content for all regular beers is known at 0.82 of our units percent alcohol. Likewise, we don't know the percent average alcohol content for all light beers, but we're taking for granted that they vary. All light beers vary 0.72% alcohol. X bar 1, on the other hand, is the average of the 108% alcohol numbers that we have theoretically averaged together, of the 83 light beer percent alcohol numbers that we have theoretically in our head someplace. They average out to 4.01. So we have X bar 1 estimating mu1, we have X bar 2 estimating mu2, we have the difference between these two things estimating the difference between these two things. In particular, if this is close to 0, then the difference here could plausibly be 0. If this is suspiciously higher than this, it might be evidence that this is higher than this. One thing's for sure, this is not suspiciously lower than this. What is our actual question? Does regular beer have a higher percent alcohol content than light beer? That should tip you off that we're interested in a one-sided alternative. Notice, by the way, that as long as you can figure out that it's a one-sided alternative, which side will more or less take care of itself, particularly if you remember that in the end, a tail is not going to be more than a half. So you can fix the error if you make a direction mistake in your hypothesis test. If you have a less than instead of a greater than, it's not the end of the world as long as you get a single tail being less than a half in the end. The mistake that will be costly, or could be costly, is doubling it when you're not supposed to, or vice versa. We are not going to double it. Everything about the wording suggests that this is a one-sided test. The rest will take care of itself. Anyway, our null hypothesis is that mu1 is mu2. The average alcohol content of all regular beers is the same as the average alcohol content of all light beers. And our alternative is, if we call regular 1 and light 2 a greater than, that the average alcohol content of all regular beers is greater than the average alcohol content of all light beers. Anyway, a single tail. From there, we just plug everything in to our test statistic formula. X bar 1 minus X bar 2. Again, which one you call which is just going to change the sign on the top and do nothing on the bottom. In this case, it's bigger minus smaller, so it's a positive z. On the bottom, it's the positive square root of something, so it's always positive. Sigma 1 squared divided by n1, sigma 2 squared divided by n2. The only thing you really have to watch out for in this formula is that you pair them off properly, right? The 0.82 goes with the 108, and the 0.72 goes with the 83. Do the calculation. Watch for intermediate rounding. It's not going to make a lot of difference in this case because we are way off the end of the chart. 9.92. So we look up the tail, well, we theoretically look up the tail associated with 9.92. Well, negative 9.92 is way off the end of the chart. So the tail in question is considerably less than 0.0002. It's not even in that league. I didn't actually write down the specific tail here, but if I pop out my calculator, it's easy to check it out, and you can see what I mean. A tail associated with a z of 994 is ridiculously small. It is, in fact, 0.220142 something. So when we say that the p-value is small, it is really small. In particular, it is obviously less than 0.002, and happening less than 2 out of 10,000 of the time through random chance. Well, what is that? 1 out of 5,000 of the time through random chance. That is pretty unlikely by anybody's standard, and it is considerably smaller than anything we're going to compare it to. In particular, if it's considerably less than 0.0002, like I said, it's 0.22 zeros, 1 something, if I remember. But in particular, it is definitely less than 0.5, 0.1, 0.1, 1%, 5%, 10% levels. At any reasonable level, 0.0002 is going to be on the small side of it. So it is unlikely in the extreme. It is so unlikely that it's virtually impossible. Well, 0.220 is impossible. If regular beer and light beer have the same average alcohol content, then the probability of, through random chance alone, picking 108 regular beers and 83 light beers and having this turn out to be as much bigger as this than it is simply through random chance is virtually impossible. It is virtually impossible, given that regular beer and light beer have the same average alcohol content, it's virtually impossible to pick samples of these sizes and have the regular beer average turn out as much bigger as it did than the light beer average. Conclusion, that is not what is going on. Remember, everything that you compute, this p-value at the end, which is ridiculously close to 0, is done under the umbrella of this assumption. Hypothesis testing is not that hard if you boil it down to its raw essentials. If H0 being true would make your sample very, very, very unlikely, then H0 is not going to be true. At least that's the way to put your money. If the null hypothesis being true means that something highly unusual has just happened, well, we don't believe that. So we reject the null hypothesis, and we find evidence of the alternative. At any sane level, we will reject H0 and find evidence of HA. It is just not plausible, having run the numbers, it is just not plausible that regular beer and light beer have the same average alcohol content. To put it mildly, we have evidence that regular beer has a higher percent alcohol content than light beer. Remember, nothing in statistics is really proof, but this particular example is as close to proof as we ever come. You'll get that later. So yes, we definitely have evidence that regular beer averages a higher percent alcohol content than light beer. And that is section 15. Just a slight redux on the ideas in section 14. If anything, the way we do it with the two sigmas known, it is a lot simpler than section 14 because it doesn't have all those intermediate steps and pooled business and rounding error. There are pooled methods we could use here, but maybe we'll talk about those toward the end of the course. Everything is a lot easier if you are able to fill in all those blanks on the bottom without having to do any estimating. The only time we ever really did that was in section 14, but that will change in the near future. That's section 14. Try the practice problems. As always, you should be able to track them down. And any questions? Pop them up on the discussion board and we'll go over things. I can post some more videos if people have questions, or I can just do things on the discussion board. The math editor is usually problematic. I try to avoid it because it locks up the browser. And when you're ready, try the section 15 quiz. Our next stop will be section 18 because we'll skip sections 16 and 17 for the time being. They have not much to do with anything. Correlation and linear regression, we can come back to those at any time. I think I would rather go on to section 18 for the moment, which is a redux of 12 and 13, the sigma unknown versions of those procedures. And we'll take a look at that next time.